Tensors. Well, we know that tensor is a very essential element in the range of physics, engineering, fluid mechanics, etc. So the basic objective of starting a new series of lectures and videos on tensor, well, one of my student, his name is Gaurav. Well, Gaurav has requested me to create a video in order to know that what is a tensor. So Gaurav, if you're hearing me out and you're watching this video has come up because of your request. And I also need to thank Gaurav sir, because tensor is something very important in physics and different fields of engineering in order to calculate stress, and it is also important to carry the elasticity, force, different ways. So this is what we are starting with today, just a schematic diagram of what is a tensor. So Gaurav, watch it out. This is a video which you have requested and this is meant for you. So before we go ahead with tensor, what we need to know is that we would be doing the minimal mathematics of tensor. We won't be dealing much into the tensor calculus. I would like to show what is the definition of tensor, what are the use of tensor. I would say a little bit about the dyad and triad of a tensor, and a little bit brush up on the skills on the areas of what is a stress tensor. So it's a good time to start. What is a tensor? So I have listed down few definitions of tensor, and I would like to show it to you, which would be important in this part. So here's the first definition, which tells that tensor is a container which contains n dimensions. Now, actually prior to the arrival of tensor, we used to calculate the different parts of mechanics as well as the properties, including elasticity and stress. But it became difficult for us when we got a real dimensional object and how to calculate. So it can be imagined as a container. That means it contains something. It is a kind of a container which contains n dimensions. It can be 1, 2, 3, it can be at n dimensions. So the second definition tells, which is a little bit more precise on it, a tensor is a mathematical object that describes physical properties like vectors and scalars. So here it tells it is of n dimension. This tells that it is a mathematical object. So we will soon see what is that mathematical object, and it describes the physical properties, which are the scalars and vectors. The third definition is basically a deduction from this part. Tensors are generalizations of scalars and vectors. So tensors do contain different type of scalars and vectors. So it is a kind of a generalization where we generalize in terms of n dimensions, and this is how a tensor can also be defined. The next definition tells that tensors are multidimensional arrays. Well, this is interesting because, as you have noted, I have mentioned in the first definition that tensors are containers, so they contain something, and we also know that arrays are containers. They also contain something. So definitely it can be called as a tensor as a multidimensional array. That means it can have any number of dimensions. Coming to the last part, which is more rigid, I would say it is a better definition of tensor. So we call it tensor is an object that is invariant. And I would like to underline this part, which is invariant. That means it doesn't change. So tensor is an object that is invariant under change of coordinates, that change and has components that change in a predictable and special manner under the change. So just to give you a basic example how it happens, this is just a very basic example. So when we are making any kind of a measurement in Cartesian coordinates, say for example this one. So when we are measuring this angle theta, or we are measuring this type of lines, which can be a vector which carries a certain velocity, compared to this, when we are moving to a spherical surface, for example, this particular line becomes a kind of a curve. Typically in general theory of relativity, this velocity then becomes a kind of a curve, and we cannot draw this line, would also become a kind of a curve. So this angle theta won't be any more theta, it will be something different. So you see now, if I want to change the coordinate of this velocity vector as it will be proposed in a spherical surface, it will undergo a change. It will undergo a change. So this change, so tensor helps us, that is an object that is invariant. So if this velocity and this velocity are changing, how will I calculate the velocity or the force or the elasticity or anything like that? So we need to get hold of something which is invariant. That means it doesn't change. Tensor is an object that is invariant under change of coordinates. So from Cartesian I'm moving to spherical or polar or any coordinates. And the change of the component, that change is predictable in a special manner under the change. That means this change is predictable. I can know what this type of change is so that it becomes easier for me for calculations. So I hope this few definitions, starting from what is a tensor. It is n dimensions, it's a container, it contains physical properties, it is a generalization of vector and scalar, and it is multidimensional, and it is an invariant object, although the components change, but it is in a special and it is in a predictable manner so that we can calculate. Well, the next important part which automatically comes is what is called the rank of a tensor. Now, Gaurav was asking me what is a rank, what is a standard. No, my dear, this is a different kind of a rank. And here I have just dotted down few important definitions. What is rank of a tensor? So here we go. A rank is defined as the number of dimensions of that tensor. So rank is basically defined as the number of dimensions, 1, 2, 3 or n. Tensor's shape represents the size of each dimension. So the shape would determine the size of each dimension. Remember, when we are dealing with higher physics, we are not dealing with only x, y, z coordinates or length and breadth and height. We can go up to 3, 4 and 5 dimensions. So this is what is called the rank of a tensor. So I think that this clears the definition. What is the rank of a tensor? So rank 0 means it is a zero-dimensional array. It has got no dimension. Example, say for example, anything which has got a 48.3 kilograms, so it has got no dimension. Rank 1 states that it is of dimension, one-dimensional array, say 1, 9, minus 7, it can be any number. Rank 2 determines it is a two-dimensional array. Say for example this part, so it has got numbers. We will soon see what are the ranks of a tensor, it becomes clear. So this is rank 2 tensor. Rank 3 is a three-dimensional array. That means it has got 3 dimensions. You see these are arbitrary numbers, however, but it determines that what is this array is all about. So this is what is called a rank. Rank is defined as the number of dimensions of that tensor. So this is what is called a rank of a tensor, and I have also showed you what is a tensor. What is the definition of a tensor? Most importantly, it would be invariant under any change of coordinates, so that it becomes easy for us to know. So now we start with the real part of tensor, and I would like to tell you with what tensor is. So this is what we start with, and we start with what is the most famous, because we started, the tensor started with Richard Hamilton, but later on it has been used extensively in Einstein's general theory of relativity. So I would just like to give a very simple, very easy definition of a usage of tensor in Einstein's general theory of relativity. So we go ahead with Einstein's general theory of relativity. So we write here Einstein's general relativity. So we are starting with Einstein's general theory of relativity, and what I'm going to do is that I'm going to just give you a simple example of how tensor is being used in Einstein's general theory of relativity. So just let me write you the Einstein field equation. Let me see if I can. Yeah. So it is. I won't go much into that. So R mu nu. This is nu. I can write it as 1/2 of R G mu nu plus lambda G, this would be mu nu and it is going to be equal to 8 pi g whole divided by speed of light times 4 t mu nu. Right. So this is basically the field equation of Einstein's general theory of relativity. This is a set of 16 equations, whatever you're watching, and this involves tensors. So whatever I'm underlining, these are tensors. This part is a tensor, this part is a tensor, and this part is a tensor. Right? Most important is this part. And this is called a metric tensor. This is called a metric tensor. I won't go it would be beyond the scope of this video to explain what actually metric tensor is all about, but just understand G mu nu is noted as a metric tensor. It is a tensor of rank 2. It is a tensor of rank 2. So tensors are also used in Einstein's general theory of relativity, and tensors used in general theory of relativity are of rank 4. That means what we do is that we can write here that this rank would be x, y, z and t. So if we consider the length, breadth, height and time, say for example we are replying this x, y, z and t, and each of this dimension, each of these components would have 4 vectors each. So we have 4 dimension, I'm so sorry. It would have 4 dimensions each. So how much it comes to? 4, 4, 16, 16, 4, 16 for 64, and this would be total of 256 components. So that stands to be pretty complicated. So when we will be learning about Einstein's general theory of relativity, these are the tensors. These are the tensors. So these are basically the tensors. This one, and this one. Right. So whatever this tensor tells, it is a metric tensor, and if we take these coordinates x, y, z and t, then this would be total of 256 components in total that Einstein's general theory of relativity looks into that. Now, tensor, as we know, it is of multidimensional. We have learnt it from the previous notes, from the previous part. So now I will give you a very lucid example. Say for example, if you have got a scalar, so we can call this as a scalar. So scalar, I can just name it as S, right? And it has got no dimension, so it would be something like 1, 2, 3, 4, dot, 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 several numbers, right? We have got a vector, which is rank tensor 1, so we can call this as vector, and I can just use the notation something like this, v1, v2, dot, 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 up till vn. This would be of rank 1, right? This would be of rank 1. Further, I would go forward in order we can develop further what is a matrix. Those who are aware about linear algebra, they would be dealing about matrix. So matrix would be something like, say we have M11, then M12, and it goes on till M1n, right? And then we have got M21, M22, it can goes up to M2n, and then we can further write it as mn1, mn2, dot, 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 and it can go up to mnn. So this is a typical example. Those who have done it, linear algebra, we can call it as it's called as a matrix. So now let us see what is called a dyad. And this is what we will start with the first part of what is a dyad, right? So dyad actually looks something like this. It will have total of 9 component vectors. So let me draw a dyad for you. Yes, so it would look something like this. So we join the edges. So this would be a typical example of a dyad. Now let me put some different colors so that you can understand. Now if I take the three portions, so we'll first take this part, right? This, the outer part of the cube. So we will have any physical object which is taking place. So this would be x direction, this would be y direction, and this would be the z direction, right? If we take the this part, that is the this middle part, so this is one. Okay, let me take the upper slice. So it would be again x, this would be on the y part, and it would be on the z part. Then we take this portion, this base portion. In the same way, we can draw three axes. This would be x, this would be y, and this would be z, right? So this is what is typically called a diode. Now we can further name the diodes. Let me draw the symbols like this. So in general, what we do in representing a tensor, we use two Greek alphabets, right? So we use one is small sigma, this one, and we also use a tau. So sigma and tau. Not essentially that you need to use this, but it is a general convention. So if I'm taking this axis, and this axis out of this, because it will be too cumbersome if I write this one. So what we get is something like this. So we get an axis in over here, right? And we use this as sigma xx, that is pointing towards the x direction. And we use it as tau xy, that is pointing this direction, and we find it this as pointing tau xz, that is pointing this direction. So this part completes this part. Then we come up with this part, the second part, the upper slice. So we draw a similar kind of a line. This one is a z part. So what we get is tau zx. So we are considering, sorry, the second part, this one. So we get tau zx. Then we get something like tau, the upper portion would be tau zy, and this portion would be sigma zz, sigma zz. Then we take the other portion, so we draw kind of a similar axis over here, and what we get is the tau yx. So this would be tau yx, and this would be sigma yy. So this would be on the upper part, this would be sigma yy, and this would be tau yz. This would be tau yz. So what it represents, that these are all the axes. So if I want to find out a typical thing which is happening around this part, we get an x-axis pointing, we get y and z. If you want something kind of a stress or anything which is finding this, we have the three axis, and we have got something like this, we have got the three axis, right? Now, in order to write this phenomena, I mean to say, if you want to write it in a matrix, now this has a typical rule, people generally get confused. So I can also use it in a kind of a format. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9. So total, there will be total 9 components, right? So I can write it as 9 components. So how I'm going to write these 9 components in a matrix form? So what I do is that I will write the 9 components just as 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are my 9 components, right? And I can put a brace around it. So first of all, generally students get confused. So there is a wonderful way in which you can write it. The first component goes this way, right? So what we can do simply is that we can write 1, 2, 3 this way, 1, 2, 3 this way, 1, 2, and 3. The second component goes in this direction. So we write 1, 2, 3, 1, 2, 3, 1, 2, 3. And this completes our matrix. So you will see it is coming up A1, 1, 2, 1, 3, 1, A1, 2, 2, 2, 3, 2, A1, 3, 2, 3, 3, 3. So just remember that the first component is going down and the second component is going in this direction. In this way, if you construct a matrix, you will never make any mistake. And higher ranks means that the indices will be more, complexities will be more. So this would be a wonderful way in which you can learn in order to draw a diode. Now, what we also need to understand is that once we have taken care of a dyad, so we also need to write those sigma part. We also need to write this sigma part in a significant way. So what I will do is that, let me see if I can fit over here with little bit small handwriting. So what I will do is that I will just put up this part. So this would be sigma xx. Let me see if I can put the camera a little bit closer to that. Yeah, this is fine. Sigma xx, then we got tau xy, and we have got tau xz. This is the first element. I will tell you why I'm showing this. Then we have got tau yx, then we have got sigma yy, and we have got tau yz. Then we have got tau zx, and then we have got tau zy, and we have got sigma zz. Right, so this is how it goes. Now just note one thing, this sigma part which I have written, okay, let me just put a different color. This sigma part, this one, if you see, it is diagonal. This part, this is a diagonal part. Why I have mentioned sigma in this fashion, the reason behind it is that if you see, sigma is in x direction, and here also sigma is in x direction, right? See here, sigma x pointing towards x, sigma z pointing towards z, sigma y pointing towards y, x, y and z. That means the diagonal part is always pointing towards the direction of the axis. All the others are different. X is pointing towards x, this part. This sigma is pointing towards z, the axis is towards z, and this sigma is pointing towards y, so axis towards y. So sigma diagonally points out to all those things. Right. Now if I'm going further into this figure and I'm trying to find out, say for example, a stress or a force or elasticity or anything like that. So if you see here, this part, sigma xx, this part is actually the first part. This part. So this actually represents this part. So you see the direction, the first indices x, x, x. That means it is happening in this s direction. Y, y, y. We will consider this part. So it is happening in y direction, right? Then we have got z, z, z. So it is happening in the z direction. So this is what actually comprises of what we called a dyad. Dyad means that we saw the cube. It has got all over 9 components, 3 axes, x, y and z. So if you want to know what is happening out here, this is the way in which we can find. The second part, this second line, comprises of any stress or any event happening in this part of the block. So it is pointing towards y. Z, it is pointing towards z. This is essentially the achievement, or I would say a significant part of what is a tensor is all about. Now, bringing a close to this, what I would also like to tell you is that what is a triad? Now, triad becomes a little bit complex, so I have to put in a fresh page and I need to show you what triad is about. So, triad is something, Einstein's equation included 4 tensor, that means it is a tetrad, which will be further complex. Let us not go into that. So triad, so what we will do is that we'll just, let me write you what we are dealing over it is what we called a triad, right? So we know that we have done scalar A, that is of rank 1. This is just something like this. Then we have got vectors which can be arranged in this direction, say A1, A2 and A3. If you want to do it further up, we can just put unit vectors with a nice hat on it, X, Y and Z. This is considered of ranked 1, that is, it is a vector. This is rank 1. Right? Dyad, we have already seen. What is a dyad? So it would be something like this. And it would contain components like A, 2, 4, 5, 3, 7, 8 and 9. And we have learnt a trick which I would also recommend for all the students. In order to write that, you can just write 1, 2 and 3, 1, 2 and 3. This is space a little bit less, 1, 2 and 3. Then you can put 1, 2, 3. 1, 2, 3, and 1, 2, and 3. So this completes whatever the diode. Now triad has got around 27 components. So how we can draw that? Well, in order to draw that is a little bit complex. So first let me show you what a diode in the diagram is. Then we will come back to the indices part. Right. So diode can be drawn something like this. I won't be going to define the indices within the diagram because it becomes very cumbersome. So let me draw it. So this one, let me join them. Okay, so what we do now, if you see that in a diode, previous to what we have gone in a diode has got only these three components, one in this, one in this, one in this. But here what we will have, this part, if I'm talking of this block, this slice, let me color it in red. Okay, this will have 3 times 3 components. That means the axis, which is generally over here like x, y, and z. This is x, y, and z. This will be total 3 times 3, 3 in number, right? So another thing is that, so it will be total of 3, 9. This part, this one, which has got an x, y, and z, will also have 3 times 3 coordinates or dimensions. This part, which is again x, y, and z, this will also is going to have 9, 3 times 3, right? And in total, it will add into 9 times 3, 27 components. So that is how a triad is. This is a triad, right? So you can understand that from the diode, we are moving up to another higher dimension, which is taking around 27 components or 27 base components or vectors that we would. So let us see how we can write it. So this is the diagram of more or less a diagram of a diode. Now we need to see that how we can write a triad. So we will use the same formula, but this time we need to be a little bit careful because we have around 27 components. So first of all, what we do over here is that we will first write the components as they are. 1, 2, 3, 4, 5, and 6. Then we move to 7, 8, and 9, right? Okay, so let us first complete this component, right? So what we will do, let me use a different color. So we will write 1, 2, 3, 1, 2, 3, 1, 2, 3. Then we will come to this next indices, which is 1, 2, 3, 1, 2, 3, and then we'll get 1, 2, and 3, right? Now when we come to the third element, initially it will run from this part to this part. It will run this way. One is this, second is this, third it will be going towards the back. So in order to have that back, what we will do, we will just put the initials as 1. 1. We are putting this all as 1. Right? So this actually is the first part. So we already got the first 9 components. So we will follow the same routine, same formula, and we will again use it as A, and A, further to A, and A, and A. So what we will do similarly, as we have learned, we will put down the components as 1, 2, 3, 1, 2, 3, 1, 2, and 3, right? And then we will move this part. So what it would be 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. Now as we are moving from this part to the back part, so the third index will be 1 plus 1, so it would be all 2. So we can safely now write all 2. All 2. So this would be basically the first component, the second component. Then we will come to the last part, which would be the last set, which we would mention it in this way. So again, let us mention it as A, and A. This is a basic formula. I think that it would be something quite helpful for people who are new to matrix. So we use again the same formula, right? So we go up and down, 1, 2, 3 is 1, 2, and 3. We go 1, 2, and 3. Now this way, so we use 1, 2, and 3. We use 1, 2, and 3. We use 1, 2, and 3. And from 2 again we are going this way, so it would be safely all 3. It would be all 3 parts. So this actually comprises of what we call a 27 component triad. This is a tensor. So this is 9, 3 plus 3, 3, 3, 3. This is again 9, this is again 9. So in total there are 27 components, and this is what is called a triad. So you see the difference between a diode and a triad. So the diode actually has only these components, which are X, Y, and Z. So we get something kind of a 9 components diode, but in triad we get what is called a 27 component. So a triad is typically used in case of crystal analysis or anything like this. If you really want to know now, say for example, the videos get a little longer, but anyway, so if you want to now typically know the stress part, or the say for example, let us take stress because it's a good and nice way to speak on that. If you want to know the stress part which is happening in this, so we have got all these components. So if we got X, Y, and Z, I'm writing it in A part. So if we got all the components, so the first part, what is in X-axis, what is happening. So we again want to know what is happening in the Y, in the second part, which is this, which is A1, 1, 2. So the forces which are happening in this direction, and is this direction, and is this direction. Similar way we can happen and handle this, which are happening in this direction. So this is again a component. So it will comprise of this slice and this. So you can imagine or write it something like this. You can imagine and something like this. This would look something like, you know, this part. This is a basic approximation. So with something like this, and then you draw a further line, and you get this, and then you got a further line, and you get a this. So this would be a kind of a triad, basic and approximation. So I think that this completes our video on tensor. This is a basic introduction. So students, I think you can now get a basic idea what strength tensor is all about. I am supposed to talk about stress tensor but it is already quite a long video. So I think I can keep the second part of what is a stress tensor and how we can find the stress vector. That would be interesting. That we can keep it in the next slide. So just let me see if we can summarize things up. We know how this Einstein's general relativity, the metric tensor, these are different ways, a diode and a triad. We have also seen different definitions of tensor, which we proceeded earlier to that, and that brings us to the end of this session. I hope you all liked it, because it is basically a simple explanation on the tensor part. So this is we first learned about the definitions. So these are the definitions which we earlier learned. But remember, the tensor would be something which is very invariant under transformational changes. We also learned what is a rank of a vector as a number of dimensions that a tensor has, rank 0, 1, 2, and 3, right? And we have also learned what is a diode, which is the first part which we learned, and how we can get the components of the different vectors, x, y, and z. These are 3 components acting in each direction, and if you want to know diagonally, we get the sigma x. That means it is pointing towards the direction of the axis. All these diodes and the figures actually points out to the stress, elasticity, or force which is happening in this particular area. So anything which is happening in y direction, we have it in z direction, we have it in x direction. And we also learned what is a triad. So triad basically comprises of 27 components, and we have seen how we can derive and write those matrices in this direction, and this direction, and one in this direction. So that brings us to the end of this lesson. Hope you liked it. If you have further queries, please you can put it up in the comment box. Stay safe and stay happy and have a nice day. Bye.